Thanks very much for the very nice introduction. And I also want to thank all the organizers for making this virtual conference possible. So today, I would like to say something about quantum simulation. And the title of this talk is Trotterization and Trotter error. So this talk will be based on some of the previous work that I did during my PhD study and also a postdoc appointment. And as Jacob just mentioned, I actually am onboarding Google this week. And I guess by definition, this will be my last time that I can claim to be a young scientist. But anyway, so the dynamics of a quantum system, as we probably know, are described by the so-called Schroeder equation. So basically, suppose we denote this evolution operator to be u of t, then the first derivative of this operator is equal to the Hamiltonian times the evolution operator. And also, we have some initial condition here, which is given by this identity matrix. So this is like a first-order differential equation. So in the general case where this Hamiltonian is it's an arbitrary Hamiltonian, then you won't have a closed form solution to this equation. But in the case where this Hamiltonian is time independent, it's always equal to this operator h, then you will have a closed form solution. So this is given by this e to the minus ATH, this matrix exponentiation. So the problem is as follows. Suppose you have a Hamiltonian, let's say h, you have some evolution time, let's say t, and basically you want to perform this e to the minus ITH up to some accuracy epsilon. Let's say maybe quantified by the spectrum norm. You have already heard of this problem in Nathan's tutorial. Well, this problem seems to be very straightforward, very easy to solve, but actually it's quite difficult for classical computers. But on the other hand, let's say if we happen to have an efficient solution of this problem, it could have applications in many areas, such as in physics, in chemistry, or even in designing quantum algorithms themselves. And actually, this problem of quantum simulation is actually one of the original motivations for Feynman to propose this idea for quantum computer. Okay, so there are many quantum algorithms that you can use to do quantum simulation. But perhaps the simplest approach is this approach based on Trotterization, or sometimes people also call it a product formula method or a splitting method, especially by mathematicians, but they're really talking about the same thing. So in any case, the setting is as follows. So you have a target system, and you assume that it's decomposed into linear combination of terms. So you have this h equal to the sum of gamma, and you have h gamma. And you assume that each term, like this h gamma, is Hermitian, and you can directly exponentiate that on a quantum computer. So you can perform this e to the minus ITH gamma. So, okay, so under this assumption, what you can do is you can use a so-called first order Trotter formula. So remember, your goal is try to exponentiate the ideal Hamiltonian, e to the minus ITH. But in many cases, you can't do that directly. But instead, what you can do is you can exponentiate the elementary terms like this, and then you just put them together. So this is called a first order Trotter formula. It's a first order approximation to the ideal evolution. So equivalently, you get an error that is second order in the time. So I'll call it a Trotter error. Of course, this is a very simple formula, and you can try to construct more complicated formulas achieving higher order accuracy. So for example, by using other formulas like designed by Suzuki or others to achieve higher order accuracy. So in any case, these formulas provide you with pretty good approximation when the evolution time is small. So what about the longer time? So let's say if you want to simulate for time t, what do? Well, you can just divide the evolution into several steps and then just apply these formulas within each step and you repeat it many, many times. So in other words, if you want to figure out the total cost or total complexity of your algorithm, well, that's very easy. You just figure out the cost per step, and then you just multiply that by the number of repetitions, the number of steps. Okay, great. So why do we care about this method? Well, it's a very simple method. I think I can basically introduce this algorithm within one slide to you. It doesn't use any ancillary qubits in principle to do that decomposition. And maybe this is a good news for like near-term application of quantum simulation. But on the other hand, it turns out that this method could potentially be very efficient, especially in the case where Hamiltonian terms commute or almost commute. There are some additional benefits. So for example, let's say if you want to simulate some system with some locality property, for example, let's say you have a 1D chain, and then you have nearest neighbor interactions, like this interactions colored with red, blue, this kind of nearest neighbor interactions. Then correspondingly, if you look at the quantum circuits corresponding to this Trotterization or product formula, you have some quantum circuit like this. It also has some kind of locality property here. And sometimes this kind of locality property can help you further speed up your quantum simulation. Some other applications, so for example, in classical simulation of quantum systems, in quantum Monte Carlo simulation, or even in areas beyond quantum computing. So this is a formula, a mathematical tool that could potentially have many applications. So I should mention that beyond this very simple approach, there have been many other approaches developed in recent years. And I think you have already learned some of them from Nathan's talk. So I won't be going into details describing these algorithms. But at a high level, these algorithms can be, roughly speaking, categorized into different groups according to their input mode. So for example, there's a common model, I usually call it LCH model. So in this case, the Hamiltonian is given as a linear combination of terms, and each term its formation can be directly exponentiated on a quantum computer. So we have already seen an example of algorithm in this model. It's this Trotter algorithm or product formula, whatever you like. But there are also some other quantum algorithms that can work pretty well in this model. So for example, there's this randomized method developed by Earl Campbell called Q-drift that also works pretty well in this model. Okay, so on the other hand, there's another common model, usually called Lcu model, where this Hamiltonian is decomposed as a linear combination of terms. And each term is unitary up to some coefficients. And then you can efficiently control these unitaries on a quantum computer. There are also some algorithms that fall into this category. So for example, we have already heard of this Taylor series algorithm or Quantization algorithm, and they can work pretty well in this LCU model. And there are also many, many other quantum simulation algorithms, which I didn't have space to list on this slide. So I guess the question to ask would be, which one should I use if we want to simulate some Hamiltonian? Well, unfortunately, I don't have a universal answer. It's a very difficult question, even for like, people working in this area. So, well, certainly I can't provide you with a complete answer within this 40 minutes talk. But in this talk, I would like to exclusively focus on one method. It's this method based on Trotterization. And well, hopefully by the end of the talk, I can convince you that this method is indeed performing very well in many scenarios. Okay, so I think that is basically all I want to mention about the background about quantum simulation. So before I proceed to the remaining part of the talk, I can maybe pause for a few minutes to see if there's any questions.
Hi, Yuan. There is one question just about what LCH stands for. Is that linear combination of Hamiltonians?
Yeah, I guess linear combination of Hermitians.
Gotcha.
Okay, so for the remaining part of the talk, I would like to talk about 4 different topics. So I will begin by saying some elementary aspects of Trotterization. I will talk about how you can implement this algorithm in the so-called quantum circuit model. And then I will talk about some ideas that you can use to somehow speed up this method by using either randomness or by using some symmetry properties of Hamiltonian. And then I plan to change the topic a little bit. I will talk about how you can analyze the performance of these algorithms. So I'll first talk about like a baby version of the analysis with scaling called a one-norm scaling. And then I will talk about how you can somehow improve, and in many cases, significantly improve the analysis by using some more properties, like commutativity property of the Hamiltonian. Okay, so great. So let's begin with circuit implementation. So one simple example we can start with is a simulation of spin models. Well, there are many spin models we can look at. So one model that we previously looked at is this Heisenberg model with some random local field. So in this case, you have a Hamiltonian, which is laying out on a 1D chain. And you have nearest neighbor interactions. So you have this poly XX, Y1, ZZ acting on neighboring vertices. And then you have this random Z operators acting on each one of the qubits. So this model turned out to be useful in the discussion of some condensed matter phenomenon like many-body localization, but I don't want to go into details. In any case, how do we implement Trotterization? Well, we can, for example, start with this term ZZ. Well, on the computational basis, we can write out the action of ZZ on the computational basis. So for example, this operator ZZ will always preserve the 0, 0 state in the 1, 1 state. But on the other hand, it will, when you input 0, 1 and 1, 0, it will always flip the phase. You introduce a -1 here. So in other words, if you somehow want to implement this operator, you have to distinguish between these 2 cases, right? So the first case is where you have like an even parity in your input state. And the other case, the second case is where you have odd parity in your input state. So let's try to use this parity information. So we first apply a CNOT gate so that we can compute the parity to the second register. And then we perform an exponential on the second qubit using this parity information. And finally, we can just uncompute the information. Well, in this way, you can implement the exponential of ZZ in Trotterization. Okay, so this is a very simple example to start with. How about some other terms? So for example, let's say if you have an XX and you want to implement that, well, this is not diagonalized in the computational basis, but that's not a problem because you can just do a basis change. For example, you can apply some local hard-mark gates so that you can rotate the eigenbasis to the computational basis. And the remaining thing is you just apply the parity computational parity computation circuits. And in this way, you can also exponentiate the XX operator in Trotterization. Okay, so I think if you think about it for a moment, you should be able to see that actually this method can be somehow generalized. For example, the general case would be you have general arbitrary polystring and you want to exponentiate that. Well, let's say, for example, you have like ZZZZ and you want to exponentiate that. Well, you can do something similar, right? So you compute the parity, let's say, to the last qubit. And since this qubit now contains the parity information, you just perform the exponentiation only on this qubit, and then you undo the computation of the parity. So Well, again, if you like, you can try to switch to the nearest neighbor case. You can apply nearest neighbor CNOT gates. You can achieve the same goal. Okay, so this is how you can simply implement trotterization of the spin systems. So of course, there could be some other systems that you want to simulate. So for example, another system that you can consider simulating is a Fermion system, sometimes appearing in the simulation of quantum chemistry Hamiltonians. So again, there are many possible Hamiltonians that you can consider. A model that we previously considered in our work is this model of interacting electrons. So in this case, you have a Hamiltonian, which is decomposed into two parts. So you have this T operator, you have this V operator. Well, the T part is further given as a linear combination of terms. So you have this creation operator, you have this annihilation operator. And for the V part, it's further given as a linear combination of occupation number operators. So what do you do with this Hamiltonian? Well, it turns out that for fermionic systems, fermionic operators, you can do something called a Jordan-Wigner encoding. So you can somehow translate the fermionic operators to spin operators using this Jordan-Wigner transformation, and you get a linear combination of Pauli strings. But remember, Pauli strings are not too difficult to exponentiate. Now you can just apply the parity computation circuit, and this will give you a very simple vanilla approach to simulate fermionic systems using Trotterization. Okay, so another example that we can look at is simulation of ladder systems, or maybe like interacting bosonic systems. Well, a simple model that we can consider is a simulation of a very simple Hamiltonian. It's a quantum harmonic oscillator, for example, studied in this previous paper by Rolando Soma. Well, in this case, your Hamiltonian consists of two parts. You have this X tilde, which is like a diagonal operator, representing the discrete version of the position operator. And you also have this operator P tilde, which is representing the discrete version of the momentum operator. It's related to the X tilde by some Fourier transform. Okay, so how do you implement Trotterization? Well, one property that you can use is the property that X tilde is a diagonal operator, right? So it's diagonal already in the basis that we are looking at. So it turns out that for these diagonal operators, you can very easily exponentiate them. So let's say, suppose we have a general diagonal operator, let's say D, and the diagonal elements are D of X. Then what you can do to exponentiate this operator is as follows. So you start with a computational basis state, let's say X, and then you first compute those diagonal elements, the binary representation in the ancilla register. And then from there, you do some controlled operation. So you condition on these diagonal information, you perform a phase, it's like a rotation on the Z-axis. And then in the final stage, you just uncompute the diagonal elements. So in this way, you can easily exponentiate the diagonal operator in the underlying basis. Okay, so I'm a little bit sloppy here because, well, in reality, these diagonal elements could be arbitrary real numbers. So you don't have a finite binary representation when you construct the quantum circuit. But that's not a serious problem because you can actually make the binary representation to be more accurate with only logarithmic overhead on the number of bits. So this is how you can implement the X tilde, the position operator. And for the momentum operator, you can do something similar after applying the quantum Fourier transform to do the basis change. Okay, so I think that's basically I want to talk about the implementation of Trotterization, elementary steps. So I should mention that this direction is actually what I should say, a very hot research direction. Many people are actually actively working on this direction, trying to propose more and more efficient approaches to implement Trotterization. And I certainly can't survey all the methods within this talk, but in the following, I would like to say something about some ideas that we have looked into to further speed up the implementation of Trotterization. Okay, so one idea that we can use is try to somehow introduce some randomness. So let's start with a very simple example. Let's say we have a Hamiltonian, this H, and it only contains two terms, so A plus B, and then we want to evolve for some time, let's say time t. Okay, so in this case, the Trotterization or product formula is not too difficult. It's just not too complicated. It's just e to the a, e to the b, and you have some Taylor expansion here. Well, on the other hand, the ideal evolution is given by e to the a plus b, and then you also have some Taylor expansion here. So if you somehow compare these two Taylor expansions, well, you see that the zeroth order terms agree with each other, and the first order terms also agree, but then there's a difference on the second order terms. So, well, in general, matrices do not commute with each other, so you can't cancel the second order terms. But something that you can do here is you can say, let's try to introduce a reversed version of the Trotterization. So let's say instead of performing this e to the a, e to the b, why not trying to reverse order? Let's try to exponentiate b first and then exponentiate a. So, okay, so if you take a linear combination of these operators, you can find that you can exactly cancel the second order terms. So in other words, you are getting a more accurate formula by doing this reverse ordering of the terms. Okay, so if you like, you can also have some geometrical interpretation of this particle. So for example, let's say if you somehow want to implement this operator illustrated by these black dots, but what you have are just these blue dots. They are not that close to the black dots. But what you can do is you can take some average of these blue dots. You get this this red dot, and of course, it's much closer to the black dot because of some triangle inequality arguments. But here we are doing something even better. So we are getting a symptotic better performance when we take the average. Okay, so there's a caveat here. You have to be careful because when you take the linear combination of unitaries, you don't get unitary in general, so you can't directly implement that on a quantum computer. You can potentially use some of the tricks mentioned in Nathan's tutorial, but that could introduce an overhead. But instead, a workaround that we propose is we try to introduce some randomness, right? So you, with probability 1/2, you either perform the original Trotterization or the reversed version. So actually, this is implementing something called a quantum channel. I don't want to tell you the specific definitions, but you can think of them as like a randomly applying some quantum operations. So in the actual implementation, you can just randomly select some classical information and you control the quantum operations. Okay, so what about the performance of this randomized protocol? Well, for the deterministic protocol, we can use a spectral norm as an error metric. Well, for the quantum channel, it turns out that the error metric will, well, one sensible error metric will be something called the diamond norm. So if you calculate the diamond norm between the ideal evolution channel and also the randomized channel, you can see that this indeed gives you a better product formula, Trotterization, with second order accuracy. So this is a very special example with two-term Hamiltonian. But of course, we can try to generalize that to more general Hamiltonians of higher order formulas. Although the analysis is more involved, which I don't want to go into details this talk. Okay, great. So this is the first idea. The second idea that you can somehow use is you try to use some symmetry properties of the Hamiltonian. So, for example, you can usually find operations that somehow commute with the Hamiltonian. So an example would be going back to the Heisenberg model, where in this case, this Hamiltonian is invariant under a collective rotation on each one of the qubits with the same rotation angle. So it's e to the minus I phi z acting on each one of the qubits. Well, using the symmetry transformations, what you can do is you just invert them between your different Trotter steps. So you have this green boxes acting on each one of the qubits, and then basically you invert them between different steps. Well, these operations, of course, won't damage the ideal evolution because they commute with Hamiltonian. But when you look at the Trotterization quantum circuits, well, they can rotate the area of Trotterization in general into different directions. So when you do the simulation, you can cancel the error in a destructive way. So you can make the Trotter error much smaller, and equivalently, you are speeding up your quantum simulation for desirable accuracy. So, okay, so this idea seems interesting, but it will be also nice to have some mathematical understanding of what is going on behind this protocol. So in the special case where all the symmetry transformations are fixed, they are equal to each other, then this is related to something called a Quantino Effect. So the protocol is as follows. You perform some kind of effective evolution, basically the Trotterization quantum circuits, and then you follow that up with some symmetry transformation. And basically, you repeat this procedure R times. You alternate between the Trotterization and symmetry transformations. So in the end, you have to undo all your symmetry transformations, and you repeat this procedure R times. Well, as R becomes larger and larger, you are, well, roughly speaking, you are kicking your quantum system frequently with the same operator. And it turns out that you can somehow approximately project your effective evolution to the called a quantum Zeno subspace. So there's a previous error bound that can allow you to analyze the error of this projection. So the error scaling is as follows. So you have a polynomial dependence on the inverse spectral gap. You have exponential dependence on the number of eigenvalues of your symmetry transformations. You have dependence on the effective norm of the Hamiltonian, and you also have dependence on the evolution time. But this is maybe not a good news for quantum simulation, because that means you have to choose your repetition to be exponentially in these parameters, which may not be very good for a realistic goal. But what we are able to show in our paper is that you actually have a better, significantly better error bound, which only scales polynomially in terms of these three parameters. So we have some exponentially improved error bounds for quantum Zeno effects. And using that, we can have a faster quantum simulation by using symmetry projection. Okay, so in the following, I would like to somehow change the topic a little bit and talk about how you can analyze the performance of Trotterization. But before that, I can maybe pause for a few minutes to take some questions if there's any.
Yeah, there is a question. So someone was curious about when you would use this randomized method over like second order Trotterization, which also has like this T cubed scaling.
Mm-hmm. What's the question?
Yeah, so like what's the advantage of why would someone use this instead of second order Trotter?
Yeah, so for the second order Trotter, you also have like this dependence on this t is tq. The error is tq. But you also have some dependence on other factors, other parameters, right? So your error will not only depends on this evolution time, but it will also depends on like the norm of the Hamiltonian, like this, the size of A and B. So if you only apply the deterministic formula, you only have one possible choice for this order of A and B. But if you somehow do the randomization, you have multiple choices for the ordering of A and B. And it turns out that that can also reduce the dependence on the size of the Hamiltonian.
Great, thank you.
Thanks. Okay, so now I would like to slightly change the topic a little bit and talk about how you can analyze the performance of Trotterization.
Hey, Yuan, I'm sorry. There's a question that came just now.
Okay.
So I thought I might just get to it now since we're here. Someone asked, what are the phases / angles in phi when you're talking about C? So I think this was the last.
This one?
Mm-hmm.
Yeah, I think you can choose arbitrary phi here. So for arbitrary kind of collective rotation, we'll always commute with the Heisenberg model. You can just do it, do a brute force verification. You can see this is this case. Okay, great. So let's change the topic a little bit and talk about how you can somehow analyze the performance of quantum simulation by Trotterization. Well, again, it'll be good to start with something simple. So let's say we have a two-term Hamiltonian, H is equal to A plus B, and we simulate that by using the first order Lie Trotter formula. Well, again, we can do this Taylor expansions. We have the ideal evolution and also the first order Lie Trotter formula. We do this Taylor expansions. Well, you see that we have already mentioned the zeroth order terms agree with each other. The first order terms also agree, but you have a discrepancy on the second order terms. So basically, I guess in the using some calculus knowledge, you can see that the function value will be the same on the 0 point, and also the first derivative will be the same because of this order condition. But then you have difference on the second order term. So you can't say something about the second order derivative. You just compute those derivatives directly, but you can't conclude that they are equal to each other. Okay, but what you can do is you can apply the so-called, I don't know, fundamental theorem of calculus or something like that. So when you want to somehow figure out the difference between these two things, the ideal evolution and the Trotterization, well, because of the order conditions, what you can do is you take second order derivative, and then you have this double integral by applying this fundamental theorem calculus twice. So you can invoke some triangle inequality, try to upper bound the size of this operator, and you get something like this after calculation. So it's given by the sum of the norm of the Hamiltonian, and you have some evolution time here because it's first order formula. So this quantity will be squared here. Okay, again, this is a very special case, but it turns out that this analysis can be generalized to handle arbitrarily higher order formulas and general Hamiltonians. So I basically summarize the result here. It's called a Trotter error with one norm scaling. So let's say we have a piece order Trotterization, and we want to simulate the Hamiltonian, give us a linear combination of terms. So the error, my claim is that it will depend on this quantity called one norm of the Hamiltonian. It's given by the sum of the size of the terms. Okay, so this is, if you remember, this is for short time evolution. For longer time, what you want to do is you only apply this formula for a short time, and then you repeat it many, many times. Let's say if you repeat that R times, well, by triangle inequality, the error will just be R times the error of each elementary step. And then basically you amplify that error by a times of R. So let's say if you want to achieve some desired accuracy, let's say epsilon, then you choose R to be sufficiently large. And you can work out the gate complexity, which is basically given by the cost per step times the repetition number. So this will give you the total cost. Okay, so I apologize that I'm probably going very fast, and hopefully you are still able to follow me. So this is basically the gate complexity of Trotterization. And we can ask, since we already know there are many other quantum simulation algorithms, we can ask how it compares to other quantum simulation algorithms. So here's a table. Well, it's frankly speaking, it's not an apple-to-apple comparison, right? So there's different quantum simulation algorithms will work in different models. So for Trotterization, you work in the LCH model, where for the other quantum simulation algorithm, they'll work in the LCU model. So it's not an apple-to-apple comparison, but I guess maybe roughly speaking, you can still do a comparison of other parameters independent of the Hamiltonian. So for example, both, I guess all the complexities will contain this factor of gamma, which is like the number of terms in the Hamiltonian. And we have some kind of one norm, which is not directly comparable to each other, but roughly speaking, you can regard them as the same thing. You have the evolution time. In this case, Trotterization is not so good. It will have super linear dependence on the evolution time. And for the error, the gap is even more significant. So you have polynomial dependence on 1 over epsilon here, where you have polylog dependence on 1 over epsilon here. So you might want to conclude that actually let's just ignore Trotterization because we have these more advanced quantum simulation algorithms. But you have to be careful about this conclusion because, I guess for one thing, they are just big O notations. We don't know the constant prefactor. Or for another thing, they are just upper bounds. And maybe quantum algorithms can perform much better in practice for simulating some concrete physical systems. So let's look at some data for practical quantum simulation. So what we did was we simulated this 1D Heisenberg model for evolution time equal to the system size and for some fixed accuracy, 10 to the minus 3. And we compared the performance of different quantum simulation algorithms. And you can see that indeed, if you only believe the rigorous error analysis presented in the previous slides, the product formula or Trotterization doesn't perform very well. But actually, if you look at the empirical performance, the product formula, Trotterization performs much better. So there's a significant gap between what we can prove for the product formula and what's their actual performance. So how do we explain this significant gap? Well, one possible explanation is that this kind of system has a lot of commutativity properties, right? So, each qubit will only interact with its neighbors. So a lot of terms will commute with each other when you take the commutators. So can Trotterization exploit this phenomenon? Well, it can. There's it's a very famous formula called the Baker-Campbell-Hausdorff formula. So it's given as follows. In the simple case, we have e to the a, e to the b. So this is like the first order Trotterization. And for the Baker-Campbell-Hausdorff formula, you have something expression like this. You have the ideal evolution here, but then you have some error terms like commutator of AB, nested commutator of BBA and ABA, and so on and so forth. Okay, so again, I'm a little bit sloppy here because I didn't tell you when this series will converge. So it could be that the series will diverge and you can't do anything about this BCH formula. But let's assume that this is not the case. This BCH formula indeed holds. And in this case, we can just try to upper bound the error using this BCH formula. one thing that you can do is you just throw away all the high order terms and only look at the lowest order error. Well, this is very intuitive, but it's actually, it doesn't quite work for many systems because in many cases, these higher order commutators can grow pretty fast. So another thing is you can try to invoke some tail bounds, but that's also not very tight because it doesn't use any commutativity of Hamiltonian. Another thing that you can do is you try to directly evaluate that infinite series for some special system, but it doesn't quite work in general. So instead, we try to prove the following results called a Trotter error with commutator scaling. So we are able to rigorously bound that the error of Trotterization will depend on this quantity called alpha computer, which is given by all the nested commutators of the Hamiltonian terms. Okay, so I don't want to mention in details about how this proof goes, but hopefully you have time to check out the paper and try to find some more applications. And there are also some possible generalizations of these results to other scenarios. So one thing that we can simply look at is try to look at how it impacts the constant prefactors of the analysis. So what we do is we redid the numerical simulation of that 1D Heisenberg model, and the new results are illustrated by this green boxes. It's indeed better than the previous analysis, and it's also pretty close to the actual performance of Trotterization. Okay, so as I mentioned, there are some possible applications of these results to simulating some quantum systems in condensed matter physics or quantum chemistry, or more generally in other scenarios. But I won't have time to present the details, but hopefully you have time to check out the paper, and maybe you can find more applications. Okay, so in summary, I have mostly focusing on this Trotterization approach, describing some of the elementary ways that you can implement this method, some of the ideas you can speed up your quantum simulation by using randomness or symmetry properties. I've discussed some possible analysis of this algorithm using either vanilla approach or maybe using some more properties of the Hamiltonian, that's the commutativity of Hamiltonian. Okay, so finally, there are some, I guess, some possible directions that one can think about for future work. So there are some generalized product formulas beyond this vanilla Trotterization. So for example, you can try to don't do this Trotterization for the entire Hamiltonian, but you can somehow try to only apply that for a part of the Hamiltonian and maybe combine them at a later time. Well, you can also try to use randomness in some other way, or maybe you can apply this LCU idea in the Trotterization. It will be very interesting to see how this generalized Trotterization can be improved using some of the techniques presented here. So I've described on the problem of approximating the evolution operator. But let's say if your goal is something different, let's say you just want to measure some observable and you try to estimate the expectation values. Well, in this case, maybe you can have more efficient way of implementing this Trotterization. Well, let's say if you want to focus on near-term implementation, maybe you have some different cost metrics. So we are discussing about the quantum circuit model. Maybe you have some more realistic models that you can consider when implement Trotterization. There are some potential connections to variational quantum algorithms. So the quantum circuits will look quite similar to each other, but not exactly the same. But hopefully there will be some intuitions from variational quantum computation that can be applied to Trotterization or vice versa. And finally, there could be more applications of this method to simulating real concrete physical systems. So for quantum chemistry, there's a very nice survey article by Sam McArdle and some other people. And there are also some very nice talks in this conference by Nathan and some other people. So with that, I want to thank all my collaborations for the nice collaboration. And thanks for listening. I'm happy to take some questions if there's time.
Great, thank you, Yuan. That was a very nice talk. We do have a couple questions. One of them is about some of the references you mentioned and whether it would be possible to get a list of these. Perhaps you could just share with us your slides, if you wouldn't mind, and then we could just post them on the Slack channel.
Sure,
would that be okay?
Yeah, I will paste the slides on the Slack channel.
Okay, yeah. Excellent.
Great.
So that should contain all the references. So, and let's see. So I think there's another question from Peter. So great talk. Are there limits you have discovered on complexity for applications in quantum chemistry and/or material science?
Yes. So,
and specifically lower bounds, he adds.
Oh, I'm not aware of any lower bound arguments about applications in quantum chemistry, but for the upper bound, I think well, there are many settings that you can consider for simulating quantum chemistry. So one setting that we considered is let's see, yeah, simulating this the so-called second quantized plane wave basis electronic structure using Trotterization. So it turns out that when you actually apply Trotterization, you get the best possible algorithm in second quantization. It's also better than some of the so-called first quantization results. So in this case, Trotterization performs pretty well. But in general, like your quantum chemical Hamiltonian will contain many terms, like n to the 4 number of terms. And in that case, maybe it'll be a better idea to apply some of the more advanced quantum simulation algorithms, like those maybe mentioned in Nathan's talk.
Great, thanks. I have a question. So, so you have these new bounds with these nested commutators, and you showed for these Ising type Hamiltonians that the empirical performance and the rigorous bound are off by like an order of magnitude. It looked like just one, which was a pretty big improvement. I guess my question is, do you know if these bounds are tight? Like, is there a model you can come up with where the actual error you will observe gets even closer to what you calculated here, or is that just not known yet?
Yeah, I guess for like constant prefect or concrete case, you can just have a Hamiltonian where all the terms commute with each other. So, this error expression will be 0 and you can saturate the error bounds. But in general, let's say if you have a nearest neighbor 1D or higher dimensional case, then the Trotterization will have a complexity that is something like NT, very close to that. You have 1 plus little 1 here. And you can prove a lower bound, which is omega of NT. So it will be a nearly optimal approach to simulate this kind of nearest neighbor kind of lattice Hamiltonians using Trotterization. But for other cases, I don't know if there could be a lower bound or optimality results for simulating this kind of system.
Great. Okay. So we have one more question, if that's okay with you.
Sure.
Could you say more about the advantage of the infinite series expansion of Baker-Campbell-Hausdorff in Lie algebraic theory? And thanks a lot for the talk. Yeah, they say the advantage. I guess I'm not exactly sure.
Okay, so
but I guess this was used for some earlier bounds, right? On was there a sort of BCH approach to putting bounds on Trotter approaches? Maybe that's sort of.
So well, this expression is an exact equality here, so you can exactly represent the error of Trotterization using this kind of formula, writing something on the exponent. But it turns out that this formula doesn't hold for all the cases. So it only for a sufficiently small evolution time. So if you want this series to converge, you need to choose a sufficiently small evolution time so that this formula will hold. And for many cases, this kind of convergence condition will be too strong for you to get an efficient quantum simulation. So for example, if you take into account of the size of all the higher nested commutators, and if you still want the series to converge, you have to somehow compromise. You have to somehow shrink or reduce the size of the evolution time for single segments. And that doesn't, in many cases, doesn't give you a very efficient quantum simulation. On the other hand, if you somehow try to use some different approach to look at this question, and you can prove that the error actually only depends on the lowest order nested commutators. And you don't have the problem of that convergence issue in BCH formula. So that will be, I think, more helpful for quantum simulation.